Welcome back to the deep dive. Today, we're plunging into a really fascinating area where biology meets technology.
Absolutely. We're looking at how our brains are starting to talk directly to machines.
Exactly. And our mission, really, for you is to understand how this cutting-edge AI, this machine learning, is shaking things up for neural interfaces, smart prosthetics, and advanced diagnostics.
And it all packed into these tiny, tiny devices.
Incredible. So what's the source material look like here?
Well, we're drawing from a pretty comprehensive review.
Yeah.
It looks at recent advancements, specifically in AI algorithms for decoding brain signals,
Okay.
and also these super energy efficient system-on-chip platforms. These are, the hardware needed for the next wave of miniaturized neural devices.
Right, the chips themselves.
Exactly. And what's just, well, striking is the sheer amount of data we can get now. Thousands of signals at once from the brain.
Thousands, wow. That sounds like a processing nightmare.
It's definitely a challenge, but also it's this huge opportunity for insights we'd never had before.
And that's the key, isn't it? This isn't just like sci-fi speculation anymore.
Not at all. These are becoming real tools.
Mhm.
Personalized assistive tech, adaptive therapies. It's moving fast.
Okay, so let's get into that potential. What can these technologies actually do? What happens when you bridge brain and machine?
Broadly, you can think of two main buckets. First, there's the diagnostic and therapeutic side.
Okay, like fixing things?
Sort of. It's more about using machine learning to fundamentally change how we diagnose and treat neurological, even psychiatric disorders.
So,
Think real-time monitoring of brain activity, neurostimulation that adapts to your specific brain patterns, truly personalized treatments.
can you give us some examples? What conditions are we talking about?
Sure, we're seeing really promising work in, say, seizure suppression or for tremors, like in Parkinson's.
So how does that work? Does it predict a seizure?
Exactly. There's this concept called closed-loop neuromodulation. The device detects the subtle signs before a seizure happens and then delivers targeted stimulation to basically head it off, stop it before it starts.
That's incredible, just automatically.
Yeah, in real time. Or for Parkinson's tremors, it can detect those abnormal brain rhythms and stimulate to smooth them out. It's adaptive control.
And you mentioned psychiatric applications, too.
Right. Similar idea. Decoding emotional states, anxiety levels, using that information to guide adaptive neurostimulation or maybe biofeedback therapy. It brings a new level of precision there.
Okay, that's diagnostics and therapy. What's the other bucket?
The other big area is prosthetic and assistive applications. This is where we decode brain signals to directly control external devices.
Like robotic limbs?
Exactly. Brain-controlled prosthetic hands, for instance, with quite impressive dexterity now. Or controlling a wheelchair just by thinking.
Wow.
It even extends to restoring movement in paralyzed limbs through things like spinal cord stimulation, guided by brain signals, and communication too, controlling cursors, typing, even speech synthesis.
That just hits differently, doesn't it? Thinking about someone regaining independence, controlling a limb with thought, or communicating just by intending to write.
It's profoundly impactful, restoring lost capabilities, enhancing daily life in ways that were, well, unimaginable not long ago.
Yeah.
And the push now is towards more complex tasks, higher degrees of freedom, more natural, nuanced control, not just simple commands.
So we've got thousands of these signals.
Yeah.
And we know we want to, say, move a robotic arm or stop a seizure. How do you actually connect those dots, the raw signals, to the action?
That's where machine learning is the absolute key. It's the intelligence layer, the brains behind the brawn, if you like.
Right, the translator.
Precisely. These ML techniques, from the more traditional ones to deep learning, they're essential for finding the hidden patterns in all that noisy neural data. Patterns humans just couldn't see.
Okay, let's break that down. What about the traditional ML models, the workhorses you called them?
Yeah, they're still very important. Their big advantage is often efficiency, computationally, memory-wise. Great for real-time processing when the task isn't overwhelmingly complex.
Like what kind of tasks?
Well, something like k-means clustering. It's really efficient for basic stuff like detecting individual neuron spikes and sorting them, figuring out which neuron fired. It groups similar signal shapes together quickly.
Okay, basic sorting. What else?
Then you have things like linear discriminant analysis, or LDA. It's good for motor decoding because it's designed to find the line that best separates signals related to different intentions, like move left versus move right.
Simple and effective.
Exactly. And for tracking things over time, like a sequence of intended movements, models like hidden Markov models, HMMs, or Kalman filters, are really useful. They constantly update their estimate of a hidden state like your motor intention based on the incoming neural signals. Perfect for adaptive BCIs.
So a solid toolkit, but you mentioned complexity. Where do these traditional methods start to, well, fall short?
They can struggle when the data gets really messy, highly complex, nonlinear relationships, huge numbers of input signals. Often, you need to manually tell them what features in the signal to focus on.
Ah, feature engineering.
Right. And that can be time-consuming and might miss important patterns. That's where deep learning really shines.
Because it finds the features itself.
Exactly. It automates that feature extraction process. It can model these really intricate patterns, temporal, spatial, much more effectively, even if it takes more computational power.
Okay, so what are the key players in deep learning for this?
Well, you have recurrent neural networks, RNNs. They're great for sequences for capturing patterns over time. So really useful for motor decoding where timing matters or spotting those subtle evolving signs of a seizure.
Right, the temporal aspect.
And convolutional neural networks, CNNs, they're masters at finding localized patterns like specific shapes or signatures in the signal, regardless of exactly when they appear.
Like image recognition, but for brain signals.
Kind of, yeah. And importantly, they can often be processed in parallel, which is a big win for reducing latency in real-time BCIs. Faster reactions.
Okay, RNNs for time, CNNs for patterns, anything else?
Graph neural networks, GNNs, are becoming important too. They look at relationships between different brain areas of the spatial dimension, how different nodes in the brain network are communicating.
So mapping the conversation across the brain.
In a way, yes.
Hmm.
Useful for things like understanding mental states or classifying seizures based on network activity. There's a cool technique called rest residual state updates that does this efficiently for EEG seizure detection.
But before we even get the ML models crunching the numbers, you mentioned preparing the data. This feature engineering step sounds pretty critical. How do we make sure the machine focuses on the right stuff?
It's absolutely crucial. Feature engineering isn't just about feeding the models. It's about making the whole process more efficient and understandable. You're reducing the sheer amount of data.
Cutting down the noise.
Yeah. Exactly. Boosting computational speed, but also, ideally, highlighting the most informative parts of the signal. What really matters for the task.
Can you give an example of how that works in practice?
Sure. There's a technique called SHA-Shapley additive explanations. Think of it as a tool to figure out which features the AI model relies on most for its decisions.
So it explains the AI's thinking.
Kind of, yeah. In one study, researchers used SHAP to identify the key neural signals, things like spectral energy or phase amplitude coupling, that were most important for decoding anxiety in rats.
Okay.
By focusing only on those high-importance features, they kept the accuracy high, but drastically cut the data size and processing time.
Yeah.
Vital for tiny, low-power implants.
Makes sense. Any other approaches?
Another one is the distinctive neural code, or DNC, algorithm. It specifically tries to find the features that make different brain states or intentions most distinct from each other, simplifying the job for the classifier later on. Less data, less complexity.
It's amazing how much intelligence goes into just preparing the data, let alone decoding it. But these sophisticated algorithms need a home, right? They need to run on something small and efficient.
Precisely. And that brings us to the hardware. System-on-chip platforms, or SoCs. Putting all this capability onto a tiny piece of silicon.
The physical device. That sounds like a massive engineering challenge.
It is. You're miniaturizing complex functions, handling huge data streams, and critically, using minimal power, especially if it's an implant or something you wear all day. Power is everything.
Let's look at SoCs for those diagnostic and therapeutic uses first. What are the demands there?
The key things are reliability and speed. You need robust decisions, very low latency, because you're often providing real-time feedback or intervention, like that seizure control we talked about.
Right, no room for error or delay.
Exactly. So one example is the neural tree SoC. It combines detection of various neuromarkers with a very low-power classifier based on decision trees, plus recording and stimulation channels. It enables those adaptive therapies for things like tremors or seizures on one chip.
Integrated solution.
Yes. Another interesting one is the Psi-CNN SoC. It tackles epilepsy tracking, but the cool part is its patient independence.
Meaning it works out of the box for new people.
Largely, yes. It uses a specialized CNN on EEG data that generalizes better across individuals, reducing the need for extensive retraining for each new patient. That's a big step for practical deployment.
Okay, now what about the SOS for prosthetics, where we're directly linking thought to physical action?
Here, the challenge often involves handling even more data signals from denser electrode arrays with potentially hundreds or thousands of channels.
More channels means more complex control.
Potentially, yes.
Okay.
Capturing more detailed information, so scalability is huge. Can the chip handle more channels efficiently? And accuracy needs to be high for smooth, intuitive control. Early attempts often struggled. Well, some early neuromorphic chips might have only handled, say, 16 channels for a robotic arm, limiting dexterity. Others had to offload some processing to an external device, adding bulk and latency. We saw systems with delays of over 2 seconds for simple movements, just not practical.
Yeah, 2.4 seconds is way too slow for natural movement. So what's changed? What's the cutting edge now?
There's been a really significant recent development with the MIL-BMI chipset. That stands for miniaturized brain-to-text BCI.
Brain to text. So typing with your mind.
It decoded handwriting, actually, which is incredibly complex. It integrates the recording chip and the decoding chip together very efficiently.
And how did it perform?
Remarkably well. It achieved accuracy comparable to running the algorithms on a computer,
Wow.
but on this tiny platform.
Mm-hmm.
And it handled tasks about 3 times more complex than other state-of-the-art BCI SOSICs at the time, like decoding 31 distinct handwritten letters.
That's a huge leap in complexity.
It is. And the kicker, it did this with over 10 times better area and power efficiency.
10 times.
Partly through using that DNC algorithm we mentioned to simplify the data, and clever hardware design like sharing memory resources efficiently. It really represents a massive step towards compact, powerful, low-energy BCIs for complex tasks.
That really does feel like the future arriving. So wrapping this up, it seems clear that integrating these neural interfaces with smart hardware-optimized ML on these tiny SOCs is driving incredible progress.
Absolutely. It's a powerful synergy. You get high-density recordings. ML finds the crucial patterns quickly and reliably.
The neuromarkers.
Exactly. And that improves everything from seizure detection, psychiatric treatment, all the way to restoring movement. It's pushing us towards these miniaturized, efficient, scalable, and adaptive neural platforms.
So next-gen BCIs, precision medicine, intelligent neurostimulation.
That's the trajectory. Self-sufficient systems that learn and adapt.
Well, that was quite the journey into the brain of the future. It's stunning to see how this blend of AI and neural interfaces isn't just science, it's actively changing lives.
It really is.
Yeah.
And, it does make you think. As these systems get more integrated, more adaptive, learning from our own individual brain activity,
Yeah.
how might that change our understanding of ourselves,
Yeah.
of human agency, decision-making, when the technology is not just responding to us, but learning and adapting alongside us?
That is a deep question to ponder. A fascinating thought for the future. Thank you for joining us on this deep dive today. Keep exploring, keep questioning, and we'll be back to unpack more incredible knowledge with you next time.